and then the machine learning models, which actually particularly which I'm interested in. So that will be the part of way of compactizing the data design. So I'd like to giving you some of example about the compactizing data. One application is machine learning based biometric security, which actually the idea is that by using the heartbeat, by using the ECG, myself and then my team members kind of developing the authentication system. So authentication system is basically the identify the people based on the heartbeat. And then I'm kind of propose, which is called the time slicing techniques. And then you need to understand the way of categorize or the way of identify the heartbeat conventionally is that they usually require to longer size of data because it have a lot of noise, and then try to extract certain features like a peak and then duration and then cycles and so forth. So they are extracting the certain values, kind of detecting of the signal. But that requires a problem to have a huge, not exactly huge, but relatively huge number of data. Like you need to take the ECG from the patient or from the people at least a couple of minutes, or longest like even couple of days they collect it. But of course, purpose is not about the authentication. It's more likely the detecting the heart disease. That's the purpose. But for the authentication purposes, still it requires to do a couple of minutes. And then the problem is that you may think about, collecting the ECG like a couple of minutes, it may not take long, but actually it depends on what kind of application you use it. For instance, you use the ECG authentication to enter the gate. Think about that. And then to measure the data, you take the couple of minutes. It's really long because compared to you tagging your ID or you tagging your fingerprint, it's just like a couple of seconds, right? So compare those kind of use cases, it will take quite long, couple of times more. But if you use this time slice technique, there are two ways of doing the time slice technique. It's just take the 15 to 30 seconds. Still it's slightly long, but it's reasonable to customer or to people can enter the building or measure the ECG based on the smartwatch. This is quite reasonable, although the time or duration of collection of data is not that long compared to the conventional ECG collection. It's have a quite good result by using this technique. And then actually this technique by itself is already published on the paper. If you are interested, I will let you know later on. It's already published 2 papers with my colleagues, and then still looking for another one later on, but that's how it goes. There is another example, which is a detecting system. It's a totally different range of the area. It's part of civil engineering, and then in the civil engineering, they're looking for some of machine learning techniques for the detection of the defect of the material. So when you look at on your left side, usually they try to collecting the data for the around 1 to the 5 microsecond. Still there are a lot of data to shows up. So it's quite interesting because when I talk with the civil engineers, I mean, so another professors who I'm working on, he comments that only the this side on your right side is gonna be the part distinct whether that material have a defect or not. So instead of take a look at whole data, I just chunk it up for this part only, and then use that one as an input of the machine, training the machine to detect whether the defect there is a defect or not. So that also quite useful because the accuracy is not that I mean, it's not like a 100%, but it's quite acceptable for the industrial standard in the civil engineering. And then currently, I'm done with my part, and then my colleagues who is in the civil engineering working on the contribution based related with this area also. And then the other one is like this is totally different one. It's not related with the artificial intelligence or machine learning, but you can think about as there's another subject of mine, which is a kind of developing the model, diffusion model for the pandemic. And then I'm kind of developing some of the important factors which never been explored before. And then that factors actually giving you the quite good shape of prediction. So this is basically a prediction model, as you can see in here. This is the formula of the prediction, which is not that bad. But this one is just conceptual. I cannot say it's really legitimate or it's really brilliant, because it's not. I do testing with the sum of data, but it's not. I believe that's not enough to generalize this formula is good, and then particular parameters which I claim is really valid. That is still need to be do the additional research on that. But for the first insight, and then the data set that I use, which is data set like early this year in the Korea data, it's a quite good shape. Accuracy is prediction accuracy is not that bad. But again, this is just an idea. But main point is that you don't need, although you can get a huge amount of data, but you don't need to use all of them. I mean, that actually giving you the additional impact or additional harmful impact, because first, number one, it requires to the additional resources to computation and then database restoring the data. That's number one. Second, usually there is in terms of data scientists, they are very or statistician. They are very important to court, or they are very common court say that garbage in, garbage out. So if your data is not, the quality of data is not good enough, then although your model, your prediction model, or your machine learning model is really good, but still your result is going to be the garbage. So that is a part of the idea underneath of this research.